Uh, t- Welcome to our chapter 6. This is our last chapter, which we are going to look at in soil mechanics. So we moved a long way. So we have seen that from our chapter 1, we found that one of the soils which you have to deal with is the swelling soil, clay soil. And so we say that this soil has a tendency that when it's saturated, when you apply a load on it, it has a tendency to change its volume under loading through either expansion when you remove the loading, or under compression, is a compressible soil, when the power water are dissipated under application of an excess loading or an excessive loading. So, and we went ahead to see that how the different phases of soil are interconnected. We looked at the void, the total volume. We see that the volume of a sample is equal to 1 plus E. And so we are going to use that application into this theory. So, and in chapter 4, if we can recall, we looked at elastic deformation. We started elastic deformation. We used Hooke's law to study how a material deforms under application of load elastically. When you don't remove that load, the material would have deformed, and you maintain that deformation, elastic deformation. Normally, it's common in what? In sand, okay? In sand and other forms of soils, but more in sand. So when you come to clays, a clay will behave in a plastic nature that when you remove a load, you want to fall back to its original path. Is that okay? As we shall see. Is that okay? For such soils also, they undergo what we call secondary. So what we call secondary consolidation, or what we call consolidation settlement. Okay, the settlement which occurs as a result of expulsion of water, as a result of expulsion of water from an fully saturated soil or clays. Is that okay? So that's what we're going to notice. It's common in soils, in bridges, where, for instance, if you're going to put up an apartment for a bridge in a swamp or over a water body, normally those soils which are common, like clay soils, which are respond to volume change when you load them. Is that okay? Through expulsion of water. So you need to know how much will this bridge deform, this abutment, or go down. Is that okay? Due to a slower process of deformation, which is what we call plastic deformation, or what we call consolidation settlement. So consolidation is a general reduction in volume of a fully saturated soil of low permeability. Is that okay? Of low permeability. Low permeability means that the depth at which the water escape is very slow. Is that okay? Therefore, the load is taken up by water and causing what we call excessive water pressure. But with time, those excessive power pressure dissipate, or water escapes, and therefore then the soil we gain is what? The soil skeleton. The soil skeleton ends up carrying the loading, and then it becomes part of what? It increases the effective what? The effective pressure, or the effective stress. And due to the drainage of some of the poor water, the process continuing until the excessive poor water pressure is set up by an increase. Remember, increase. How do you determine that? If you have a point load, you load our soil, and this point load of Q will cause an increase at certain depth here of a stress, an increase in effective stress. Is that okay? So we looked at in chapter the different methods of how to predict this increase in effective stress. And the simplest case is that of a one-dimensional constellation, in which a condition of zero lateral strain is implied or implicit. The process of swelling, the reverse of consolidation, is a gradual increase in the volume of a soil under the negative excess poor water pressure. So we are going to see that when you load this soil vertically, we shall see that there is no zero. So from that we can determine the coefficient. We can use this distance to determine the partial ratio. Which was a very important parameter in the deformation of soil. Okay. A consolidation settlement is the vertical displacement of the surface corresponding to the volume change at any stage of consolidation process. Now there will be change in volume. So you're going to find that. Now consolidation settlement will result, for example, if a structure is built over a layer of saturated clay, or if the water table is lowered permanently in a stratum overlying a clay layer. So when the settlement occurs, when there is reduction in volume of water, okay? When the water reduces, there is a depression. This is common. Okay? When the water reduces, there is settlement, a reduction in volume. Okay? On the other hand, if an escarpment is made in a saturated clay, even the reversal of settlement will result in the bottom of the funnel due to the swelling of the soil. I've already explained heaving. Heaving occurs when this pressure Heaving we said heaving occurs, if you remember in our last discussion, when this effective stress when the effective stress, if this area of the depth is divided by the uplift stress, or the up thrust, or the uplift due to a certain pressure difference, or due to the increase in volume of water to this height, it will cause, if this is less than 0, so less than 1, if this is less than 1, okay, if this is less than 1, what happens that there will be swelling. Okay, the soil with the water, with this pressure of water, since the resistance offered by the soil skeleton, the effective stress is less than the applied stress, which is the pushing force, or which you call the tensile, or the tensile on the tearing stress coming down will push the soil apart into creating what you call an eave. Is that okay? Or the soil will separate. Is that okay? The soil will separate, and so then we have what you call piping or eaving. Is that okay? So in a case in which in cases in which significant lateral strains take place, there will be an immediate settlement, to call our primary deformation, due to the deformation of soil under undrained conditions. In addition to the consolidation settlement, immediate settlement can be estimated using the results from elastic theory. As we said, using the Hume theory, the constitutive model, which we said the constitutive model relates the effect to the impact. Remember, effect is the deformation. So our deformation matrix is equal to 1 over E into something times the stress in Z. Is that okay? Now this equation, using this equation, as we discussed it, you find that this is the effect, this is the causative, or the causing, which you cause. Now, what cause using this model here, the processing, this is the output, the input, this is the modeling. We call the constitutive model gives what called a deformation. Is that okay? Or the strain. From the strain, we can determine the total deformation using what? Now, for this, we covered it. Now what we are going to clarify is what called the secondary, this primary or secondary consolidation. Now, the process of consolidation in situ can be monitored by installing the piezometers to record the change in water pressure with time. Now, for this piezometer, remember, we look at the piezometric surface. They measure the reduction in that line, the grading. Is that okay? If water, when the pressure of water dissipates, the volume in this piezometer they install will be reducing. Remember, this piezometer, they measure the level at which the water would rise if there was no confinement, or there was no confinement from a clay. Is that okay? So this pressure can be monitored. Now, that's why when you, for instance, if you do apply a surcharge. So, for instance, if you are constructing a swamp, and you want to construct what? Road pavement. Okay. We are going to see that. So you apply, you pre-consolidate. Pre-consolidation helps in applying what we call a pre-consolidation stress. So that what that pre-consolidation stress will cause consolidation through expulsion of water from that material. But you can monitor that the water is being repelled by installing a such. If you have seen where people constructing swamp roads, they put such points in which to monitor water. Make sure the water goes down. So when the water goes down, that consolidation has what? Has occurred. The magnitude of settlement can be monitored by recording the levels of suitable reference points on a structure or in the ground. So another thing, if you don't use piezometers, as you are using the piezometers to monitor water power pressure, but also you can put benchmarks. Is that okay? You can put benchmarks to be able to determine, to ascertain the vertical difference which has occurred as settlement was taking place. Precise leveling is essential, therefore. Working from a benchmark which is not subjected to even the slightest settlement. So you put, normally this benchmark are fixed, maybe you can fix on a bridge, or if you are constructing a road, you can fix it on, you can fix it somewhere, you can fix it on a point which is not subject to what? Settlement. Is that okay? You can fix a reference point to a known benchmark. To a known benchmark or a survey point. So from that point on, that is not moving or it is fixed. So it can monitor the differences between the readings you take a month, every after 6 months or every after 3 months. As it's only through such measurement that the adequacy of the theoretical methods can be assessed. The time that settlement has occurred. So how do we determine this? We are going to see how do we determine the consolidation. Is it okay? To predict the consolidation. So the first thing in the laboratory, you need to first determine the compressibility properties of the soil you are studying. Is it okay? So you can do that under the odometer. So in the odometer, you'll be able to get two parameters which are so important in determining the vertical compression. This parameter is what we call the coefficient of volume change. The coefficient of volume compressibility, MV. Is it okay? Another thing, which is the reverse of stress. Is it okay? It is the stress applied on the unit meter. Is that okay? So unit meter is what you can carry, so it's a measure. So another thing is another one, what we call the compression index, CC. So these parameters you can determine them by doing what we call, by carrying out from the lab, from what we call the odometer test. Is that okay? So in this odometer test, as you can, if you look at the videos which are attached into your model in the platform, able to determine that you need polar. So you pick a sample which is undisturbed, saturated, to make it, you saturate it with water, as you can see in the experiment. These are porous. Now for this filled with water, you see now for this material should be saturated. Remember, so you put porous, two porous rocks. We have to make sure that these surfaces in which you put out the confining ring, they're smooth, so that they don't provide any resistance to movement or any friction. Instead of these, they're smoothened through application of a smoothing material. Is that okay? So when it's smoothened, then when you apply a loading onto this, obviously this other side, they experience zero strain. So what do you have? So you have a sample, with a stress in Z. Is it okay? But and strain, there will be a reduction. Okay? So there's also a strain in what? A strain in Z. But what happens that in a strain in X, a strain in X is equal to 0. Okay, and also a strain in Y is equal to 0. Is that okay? But another thing about that, but since there is a reaction, when you apply a force here, there will be a reaction or a pushing force from the ring. Is that okay? Counter the reaction action in this other direction. Therefore, there will be an induced stress. Normally, you have to put your stress what? what do you call them? Sensors, stress sensors. Okay? When you put a stress sensor, you'll be able to measure a stress in X, which is equal to a stress in what? A stress in Y. Okay. Now, if you apply our constitutive model, okay, and we assume these are principal stresses, therefore the shear stresses are 0. So we can simply, now for the deformation, you can take the deformation in Y is equal to stress in Y divided by Young's modulus minus Poisson ratio into Poisson ratio into stress. This is in Y, in X, minus Poisson ratio stress in Z. But we say that this is equal to 0. Is that okay? Now for this is 0. Okay? So now this is over E, Young's modulus. There's no, it's the same, Young's modulus is the same. So we remove that, divided by Young's modulus over 60. Okay. Now for this, if this is order for this is okay, this also cancels out. So what do you find? You find that we say that this is equal to this. Is that okay? So if this is equal, now this can also be Y, since this is equal to that. Is that okay? So you can find that stress in Y minus Poisson ratio against Poisson ratio times stress in, remember this is now we replace this with Y, this is since are equal, minus stress in Z. So when you put this into brackets, when you factorize out stress in Y, so we shall have 1 minus Poisson ratio is equal to 0, this is equal to 0, is equal, minus, so this is Z, sorry, supposed to be Z, minus V, stress in what? In Z. So our Z is a vertical, and this is our Y, or X is the lateral what? Is the lateral stress. Is that okay? So if we make is Z over Y, if we take this other side, we shall have that. We shall have that stress in Y into 1 minus Poisson ratio is equal to V into the vertical stress. It's the lateral stress, the vertical stress. Is that okay? Which is our Z, stress in Z. Is that okay? So if you get our ratio, this come this side. If we make Y over Z, so stress, lateral stress over vertical stress Z. So if then we take this other side is equal to V divided by 1 minus V. Okay. Now for this ratio here is what we call the K naught, is equal to K naught. The lateral earth pressure at rest. Is that okay? Which is the ratio of lateral strain over vertical strain. Now for K naught, we can say that K naught therefore is equal to V divided by 1 over V. But this one is also equal to 1 minus sine theta, where theta is the angle of friction. Is that okay? So from these relationships, we can be able to predict. For instance, if you have sensors, if you want, for instance, if you have sensors here, you can this sensor you can determine the lateral stress. You can sense and time you give you the magnitude of the lateral stress. Then from up here, you can determine the magnitude of with this area, you can determine the magnitude of the vertical stress. Then from this relationship, you can be able to determine the Poisson ratio for that soil. Is that okay? You can determine the Poisson ratio of that soil. So the upper polar stone, which can move inside, this one can move inside. Okay, it can deform as water is being dissipates. It is fixed below a metal rod cap through which a pressure can be applied to the specimen. So we have a plastone we can fix it below a metal cap so that it can move down. Now when it moves down, it allows water to percolate through. Is that okay? And to make sure that the water is under the condition of such complete saturation, by also dissipating or reduction of pore pressure through repulsion of water or expelling of water. When water is expelled out, not repulsion but expelling of water. The whole assembly sits in an open cell of water to which the pore water in the specimen has free access. Okay, water can then move in and move out. Under loading, it will be, then under unloading, it will be moving in. The ring confining the specimen may be either fixed, clamped to the body of the cell, or floating, free to move vertically. The inside of the ring should be smooth, polished surface to reduce side friction. The confining ring imposes a condition of zero lateral strain on the specimen. Therefore, the ratio of lateral to vertical effective stress being K naught, this ratio here. This is lateral strain, this is a vertical strain, gives you K naught. K naught, the coefficient of earth pressure at at rest. This is a very important coefficient. Is that okay? The compression of the specimen under pressure is measured by the compression of specimen under pressure is measured by means of the dial gauge operating on top of the loading. So we can measure the compression. This loading, it can be determined from such. Then if you have sensors here, you can determine the lateral stress, which in the end can help you determine K naught, which help you can determine the partial and the partial ratio. Therefore, the initial pressure will be determined on the cell and will depend on type of soil. Then a sequence of pressure is applied to the specimen, each being doubled to the previous value. So every after 24 hours, each pressure is normally applied for 24 hours. In some exceptional cases, you can do 24 hours, may be required. The compression readings may be observed at suitable intervals during this period. At the end of the incremental loading, when the excess water pressure is completely dissipated, the applied pressure will be equal to the effective vertical stress in the specimen. That will be then when you apply it. Then after that, the results are presented by plotting the thickness or the percentage change in volume of a specimen or the void ratio at the end of each increment put against the corresponding effective stress. Okay, according against the applied or the loading. Is that okay? So how do you do this? So this is the initial specimen. Then when you loaded it, it will reduce to this height. Therefore, this minus will give you the change in H. Is that okay? Therefore, remember we said that we are doing change in volume divided by original volume is equal to, remember the area is the same. Is it okay? What is changing is the H. Therefore, which will be equal to A, change in H, divided by A, original H naught. Now for this A will cancel out, so we shall remain with. Now for this one, remember our volume is equal to 1 plus E. If the initial volume, is that okay? 1 plus D naught. That's our initial volume, total volume. The way it is a sample. That is initial. That's the initial volume. Then the next volume. Now for when there is application, at the end of application of load 1, effective stress 1, after 24 hours, when all the water dissipated and there is this reduction, then there will be a change in void. Is that okay? Now for our volume 2, our volume 1, after application of the load, our volume 1 will be equal to 1 plus E1. Okay? Now for the change in volume is equal to, change in volume is equal to 1 plus E naught minus again 1 minus E1. This minus that. So you find that this one will cross out. Therefore, our change in volume will be equal to our change in volume dV is equal to E0 minus E1. Is that okay? And E0 minus E1 is change in what? Change in E. So we substitute. Our volume is this one. Therefore, we can now for this can be represented. Now for this one, that it goes that. Remember, I said it's change in E, change in H, sorry, which comes to this A cancels out, divided by H0. We said is equal to change in volume, which is change in volume, which is equal to change in E from here, change in E over 1 over total volume, which is H0, total volume, which is equal to 1. Remember, this one, this change, this one, this is V, which is B H0 plus E. E0, is that okay? Is equal to. So when you look at these two values, now for when you sub now for to if you bring this side, you take H0. If you bring change in E, or change in E. So if you may want to make this a subject, so if you bring this one here, this one will go up here. You cross multiply this. This comes here. And this goes up here, which gives us such an expression. Is that okay? Now, if we can now for our purpose is to determine E. Is that okay? Our purpose is that now for this one can be determined. Okay, H0 is known on the sample, so our purpose is to determine E. By each change, every application of the load can determine the H, because the H is equal to the original length, to original height minus the new height. The new height, is that okay? So if you determine, if this can be determined after application of each load after 24 hours, you can determine the change. You can determine how much it has it has moved down. Is that okay? Then with this, then you can from this expression be able to determine dE. Why do you need dE? Because we have said that from this expression that we have explained that from this expression we can say that, remember we said E0 minus E1 is equal to change in E. So if you know E, then we will be able to determine. You'll be able to determine, because therefore our E1, which we need, ever after experiment, the new void ratio, ever after the experiment will be equal to E0. E0 is constant, the initial is known, E0 minus change in what? Change in E. The change in E will be determined from such expression, because if you have the change in E0, you can use this expression. This is known, this is known. Okay? So you can put this. That's how we can. Then we plot. After determining we plot, we shall have a plot of E over the effective what? The effective stress. Okay? Over which will be a curve. We shall have initially when the effective stress was 0, E was high. So when you increase the effective stress, E goes on what? The void ratio goes on reducing. Is that okay? It goes on reducing. So we finish this part. Then the next part we are going to look at what about in terms of H? You can predict also E in terms of H. Instead of determining this expression, passing through this idea, remember our purpose was determining E1. Every after, because we are reporting E against what? So it's very easy also. Why? We can come up from this expression. How do we get this expression? HS can be determined from this expression. The volume of solids is equal to mass of solids divided by G. Now, the mass of solids can be determined from our experiment. We know how to determine the mass of solids times density of water times specific gravity. Is that okay? But what is mass? What is volume is equal to height times the area. Which here, therefore, we make HS the subject by determining therefore the equivalent thickness. The thickness of solid HS is determined from this equation. Is that okay? Through the mass of solids can easily be determined from the experiment. You can easily determine the mass of solids. Is that okay? You just have to try the soil and determine the mass of solids. Then you can the GS is known. That the density of water. Then the concentration area. You can also determine it. Is that okay? Of the mode. So you can determine HS. So our purpose now is to determine H1. So H1 is very easy. You remember we said that from this experiment method E, what is void? Void ratio is equal to volume of voids divided by volume of solids. Volumes of solids. But what is volume of voids? Volume of voids is equal to total volume minus volume of solids divided by volume of solids. Is that okay? So what is volume? Now, if the area is the same, this volume here, the VH, will be the height, this height here, the volume. Height times, remember, volume is equal to height times area. Now, if the area is the same, then the area will cancel out. So remain with height 1 minus the height of this. This will know that HS, which will be also the area is the same, the concentration area is the same, and so A disappears. Therefore, which one will be equal to? Which will be equal to area times height 1. Because we are using this height 1. Once the remaining void, is that okay? We are getting fine, get the remaining volume after application of the load. What is the remaining volume now of voids? Is that okay? Minus A times HS divided by A area, question area times HS. What happened? The A will disappear. So the A will disappear. Then we shall remain with H1 minus HS over H. Therefore, instead of using this other procedure of predicting E from this equation, but if I determining this is already known, determining this by each load increment after 24 hours. Then also you can determine to decide now to measure the heights. If you can determine the heights of the sample, every after the remaining height. This is if you determine this height 1, then you can use it for each increment to determine E. Okay, the initial one E naught, you know it. Initial E naught when there is no is the initial one before application of the load will be equal to H total height of the sample H naught divided by HS divided by HS. Mind you, the height of solid is not changing. What changing is the water. So from this simple equation here, you can determine the height, because it says we know how to determine the mass of solids through determination of water content. Then you can determine the water, which is what the mass of solids which is remaining. Is that okay? So you can determine the mass of solids. So from that you can be able to predict and move forward. So how do we plot? Remember, this is I said the soil is what? We are in elastic soil. That when you load the soil, when you start unloading, it doesn't go back to its what? This original shape. Is that okay? It doesn't go back to its original shape. Therefore, it expands, then it reconstructs, going through, because it is what? A plastic. It is an elastoplastic material like the soil. So therefore, you plot E. Therefore, this is loading. Is that okay? This is loading. This is unloading. Then also reloading. They give the same shape. Okay. Obviously, to go to the constant, then after it will obviously tend to go. It will reach a critical state, and any application of load, it will give you a constant what? A constant a constant strain at the critical state. Yeah, shall reach what we call a critical state of soil. Where any other application doesn't cause any major deformation, change in what? Change in strain. Is that okay? Which that's why it goes back to this. Even after unloading, then you start to after unloading, then you load it again to goes back to this line, then this line will become constant. To become now this is for a normally consolidated soil. For normally consolidated soil.